Okay, so welcome back. We are continuing with substrate integrated waveguide, and for substrate integrated waveguide we have seen that we have one more additional reason of loss, and that is the leakage loss from the sidewalls. So we want to keep it minimum because we introduced SIW for a lower loss compared to other printed lines. So here we are plotting in this graph. We are doing loss study. We are plotting the loss in dB per lambda. Lambda is the guided wavelength versus different p value, p by periodicity by lambda, for different diameter of this periodic via. So for the first case, d by lambda equal to 0.05, and for this last one, d by lambda equal to 0.20. So for a given periodicity, d is higher. So that means what? We are decreasing the gap, or we are expecting lower leakage loss through this gap. So as you can see from this plot, so these plots are obtained by using full wave simulator, which give you very accurate result, almost similar to measured result. So for a given periodicity, then if I keep on decreasing d value, the h to h separation increases and leakage loss increases. So we have higher loss. So for a given d, if I increase periodicity, again we will be facing the same problem. Now if I define the loss by a suggested value, let us say 0.05 dB per lambda, then we can't consider any value on top of this red line. We have to consider only the bottom of the red line. So it determines some design criteria. We have some limiting value of d, so below which we can't use, otherwise there will be higher leakage loss through this gap between two metal via. Here is the plot of alpha and beta, measured alpha and beta, and also predicted alpha and beta by using full wave simulator. So it is drawn for a SIW designed in a substrate of dielectric constant 9.9 and tan delta 0.0002, and we are using copper as the metal, and the dimension you can see here. The d diameter is 0.635 millimeter, periodicity is approximately 1 millimeter. The separation, midpoint to midpoint via separation for the side walls, it is approximately 4 millimeter, and thickness of the substrate, it is 0.254 millimeter. And you see the measured response and the predicted response by full wave simulator, it is very close, and its cutoff frequency is nearly 15 gigahertz. So at cutoff frequency, what we expect? The total loss alpha, which is due to the three reasons, it will be infinity, and then it decreases. And not only that, do you remember for rectangular waveguide, when we have both dielectric loss and conductor loss, in that case loss is approximately minimum at 1.5 times of Fc. Here also we are expecting similar effect for SIW. So alpha has minimum value approximately at 1.5 times of Fc, then it slightly increases. And the beta, so beta is equal to 0 at the cutoff frequency, so it shows clearly the cutoff frequency is 13.5 or 13.8 gigahertz, and then at higher frequency beta changes linearly. So if I consider very close to the cutoff frequency, this line will be dispersive. If we move away from the cutoff frequency, dispersion effect will decrease. So we have a closed form expression where attenuation is minimum. So approximately it is F naught, where the attenuation is minimum, it is 1.5 times of the cutoff frequency. And one more interesting thing, that SIW, it supports both slow wave and fast wave. So, if I plot beta by k naught instead of beta, so then how the plot it looks? Let me plot it. So, we are going to plot beta by k naught, normalized beta versus frequency in hertz. So, beta by k naught, let us say it represents equal to 1.09. So, if by beta by k naught is less than 1, that represents Vp is higher than C or fast wave. So, for rectangular waveguide, if I plot beta by k naught, let us say this is the Fc, then it varies according to this dotted line. It will be always a fast wave. This is for a rectangular waveguide air field without any dielectric, or epsilon r, this is equal to 1. Now, for SIW structure, we have some dielectric material always present. So, we are loading it by epsilon r, and now let us say we have adjusted the width so that they are having similar cutoff frequencies. Now, for SIW, if I plot beta by k naught, then it supports both slow wave as well as fast wave. So, for this part beta by k naught is more than 1. So, it represents the slow wave region, and the left hand side part for which beta by k naught is less than 1. So, it represents the fast wave region. So, what we see then, SIW, it supports both fast wave and slow wave. So, this is not just for SIW. For a air field rectangular waveguide, if we load it with some dielectric material, for that case also we will see that it supports both fast wave and slow wave. Now, the design graph, it is showing P by lambda c versus D by lambda c plot. P is the periodicity, D is the diameter of metallic via, and lambda c, this is the wavelength at cutoff frequency. Now, this right hand side bottom part, you see it, this part in this region, it represents D is more than P. That can't happen. For physical realization, D is, it always should be less than P. So, the limiting factor is D is equal to P, and we have a straight line for that. So, this design graph, it shows we have solution only in the upper half of this part. Now, one more factor, if we increase P for a fixed D, that means we are increasing the separation, H to H separation, leakage will increase. If we use some suggested value of leakage, let us say the normalized leakage constant alpha L by k naught, it should be less than 10 to the power minus 4. To keep this leakage smaller than this value, we can't use this left hand side part, because for this part this gap between two metallic via is too big and we will face leakage. So, then the region of interest is shown by this yellow line. Now, this we have a limiting factor again, which is coming due to the band gap effect. You remember P, it should be less than lambda by 4 at the upper edge of my band of operation. So, this upper region is limited by band gap region. Similarly, we defined one lower region. So, this is, it represents the over perforated regions, because if we drill too many vias, it will become fragile. So, it is not mechanically rigid. So, to avoid that, we are defining one more forbidden region, and so as a result you can choose any D and P value to realize your SIW structure. The solution you should take from this yellow part only. So, now we know enough theorems. So, let us see then what are the design criteria. So, design rules are described here. First rule, it comes from the band gap effect at the band edge upper cutoff frequency. P by lambda c, it should be less than 0.25, already we discussed. And then to keep the leakage loss minimum smaller than this suggested value 10 to the power minus 4, it can be shown P should be less than equal to twice D. So, at least D should be half of P then. And for mechanical rigidity, P by lambda c, it should be more than 0.05, we defined it. So, basically this design rules, it describes this region of interest. Next, we have to calculate the effective width. Once we have the effective width A effective, then we can use the rectangular waveguide formula. So, A, it represents the physical separation, midpoint to midpoint separation, and A effective, it represents the effective separation between the two effective electric side walls. Now, let us see how this A effective, it varies with it varies with the periodicity P and the via diameter D. So, we are plotting again P by lambda c versus D by lambda c, and you remember this is the region of interest. So, left hand side in some region it shows that A effective by A, it is actually more than 1, but we are not using this region, because we know if we choose any P and D from this region, then we will face high leakage loss. So, we have to choose a solution from this yellow region, and this in this yellow region we see that K, A effective by A, it is always less than 1, as we predict from this formula. A effective, it should be always less than 1. So, why the calculation of A effective is so important? Because once we have the expression or the actual value of A effective, then you can use all the formula you learned for rectangular waveguide. Next is design steps. So, let us say for any given application, now you are asked to design one SIW. That means you have to choose a substrate first, and then you choose your periodicity, you choose your D, and you choose the via to via sidewall separation A. So, already we have the design rules, we can use those design rules to obtain the physical parameters for fabrication. So, let us start with the first step, calculation of A effective. Once we have A effective, from that we can calculate the physical separation A. So, how we calculate A effective? Let us say the suggested band given, lower frequency and upper frequency you already know, then you can calculate the mid band frequency of interest, that is simply upper cutoff plus lower cutoff divided by 2. Then we keep the minimum attenuation point at the mid band frequency. So, if your mid band frequency is f naught, in that case then we can choose fc value, that is equal to f naught by 1.5. Once you have fc, you can calculate A effective. So, A effective equal to approximately lambda c by 2 square root of epsilon r. Now, we have A effective, so we can use this formula to calculate what is the physical separation A. Next, we have to choose D and P. So, already we know the requirements, P should be less than equal to twice D, and P by lambda c, we have a lower limit and upper limit, it should be within 1 by 5 to 1 by 20. If nothing is specified, we choose a midpoint value, P by lambda c equal to 1 by 10, and then already we calculated A. So, now we have all the parameters A, P and D. How to choose the substrate? If I increase epsilon r, the structure will be compact because A effective will be smaller, but at the same time its power handling capability will decrease and loss will increase, because with increasing epsilon r you are decreasing cross sectional area. Not only that, if I choose a higher thickness, that means we are increasing cross sectional area. So, we are increasing the power handling capability as well as we are decreasing loss. So, depending on the substrate available to you and requirement, application requirement, you have to choose your substrate wisely. What it should be the epsilon r, what should be the thickness of the substrate. Let us take one example. You are asked to design one SIW for Ku band application. So, my band of interest is Ku band 12 to 18 gigahertz, and the substrate already given, it's the available substrate is 1.58 millimeter thick RTD 5880 substrate, for which epsilon r this is equal to 2.2 and tan delta 0.09. Now, we are going to fabricate it by using mechanical drilling, and the drill bit availables are 0.5 millimeter diameter, 0.8, 1, 2 and 3 millimeter. So, you have to choose a proper drill bit and then fabricate your structure. So, for that you have to calculate then D, P and A. We can utilize these 3 steps and then one by one you can calculate. So, what should be the first step? The first step is the calculation of A effective. Now, the band of operation is given 12 to 18. So, mid band where we will keep the attenuation minimum, it is coming then 15 gigahertz. So, FC is 15 by 1.5, 10 gigahertz. Then calculate what is A effective at 10 gigahertz. So, once you have that, you can calculate D value and P value. So, here I am showing the calculated values. A effective is 10.1, P we chose lambda c by 10, it is coming approximately 2 millimeter. Then the chosen values are D equal to P by 2 to keep the leakage loss minimum. We are considering the limiting value, and the drill bit then we have to use 1 millimeter, and the corresponding A according to this formula it is coming 10.6. So, midpoint to midpoint physical separation it should be 10.6 millimeter. So, if you fabricate this structure in this substrate, it should support 12 to 18 gigahertz band applications. So, before going to next topic, which is waveguide, dielectric waveguide, let me discuss about the fabrication procedure, how we fabricate in printed circuit board technology. We can fabricate SIW structure and as well as we can fabricate microstep or CPW structure. So, 2 methods usually we use, one is chemical etching method and another one is milling method. So, in chemical etching method, what we do, first we use some photosensitive material on the copper cladding and then we print some mask, it can be negative as well as positive. So, here in IIT Kharagpur we design negative. So, you have some metal patterns you want to obtain it, and the unwanted copper part we have to etch, so that only the required or desired metal part will be remaining. So, now for this undesired metal part we will print in black color, then we will keep this mask on that photosensitive pasted copper clad, and then we keep it under UV ray. So, all the open part, it will be exposed by the exposed part, it will be its chemical property will change under UV ray, and then we use some sort of dye, and that will change the color of this exposed part. So here we are showing some example here. So this is a chemical bath, and when we immerse this copper cladded structure inside dye, you can see the microstrip part which is actually desired. So its color is changing, and then once we keep it in a etching solution like ferric chloride, then the unexposed part, copper from this unexposed part will etch away, and only the copper in this part will remain. So that's how we can realize the top metallic pattern. We have one more method, it's using mechanical milling. We have some computer controlled machine like this. In IIT Kharagpur, we are having one LPK and one MITS machine. So inside this machine, what we have a drilling machine like this, and it can also do milling. We have different types of bit for different purpose. For milling, we have milling bits. For drilling, we have drill bit, and to cut away a substrate part, we have also substrate cutter. And what it does, simply it mill or it simply rub away the unwanted copper from the top surface. So that's how we can obtain the required metal pattern, and this is fully computer controlled, and the fabrication procedure is very accurate. Even we can fabricate a thin line as thin as 50 micrometer, and with a metal to metal edge separation as small as 50 micrometer. So frequency up to 110 gigahertz or even up to 140 gigahertz is possible. Now how to obtain the vias for SIW or for ground backed CPW lines? So what we do, again we will be using those now drilling bits. So we will be having some air vias by using this drilling bit. Now once we fabricate air vias, we will be having exposed dielectric. We need some metallization on the dielectric. We can't use electroplating technique directly on dielectric, because as a starting material we need some metal for electroplating. So we use some initiator which will deposit a thin layer of copper a few nanometer on the surface of this dielectric, then we put it for electroplating. So here this figure is showing how we fabricate plated through hole, or it calls PTH tank. So once we have the drill vias, we use initiator on it, and there is one more technique. We can also use sputtering or evaporation to deposit a thin layer of thickness a few nanometer of copper or aluminum or gold. So once we have that thin layer of metal, then we put it for electroplating inside this tank. And what is the minimum thickness of copper we need? That should be at least 5 times of the skin depth at the lowest frequency of operation. So here we are showing two different types of via. By using this PTH, basically what we obtain a via like this right side. So you can see the hole. So from one side of the substrate you can see the other side, because inside we have air, and on this cylindrical surface we have copper deposition. You can see this copper layer from top view. And left hand side, one more via fabrication procedure. In this case we used some metallic paste. We have some silver paste or gold paste. So inside we put them and then put it in oven. Keep it for a few hours, then it will become solid. So left hand side it shows solid metallic via, but its fabrication procedure is expensive and time consuming. So next topic, we are going to start waveguiding structure using dielectric only. Already for the surface waves we have seen that a dielectric slab itself can support electromagnetic wave propagation, and dielectric slab backed by ground plane, that can also support electromagnetic wave propagation. But if I use a dielectric slab, the wave is not confined to any channel, it will spread throughout the surface. So, that is why we call it surface wave. Now, the waveguide, if I want to design any guiding structure in dielectric technology, so we need to design a channel first. We can simply take a thin layer of dielectric material. Instead of slab, we have to consider a rectangular cross section, and then it can support wave propagation. What is the advantage? So, for this case, we can minimize conductor loss. So, that was the main problem for printed lines. So, instead of then printed lines, we can use these different types of dielectric guides with reduced loss. So, here are some examples. The first one is called the image guide. You can see one dielectric channel, it is sitting on a metal plane which is used as the ground. In the second example, we have actually two different layers of dielectric. The first layer of dielectric material, dielectric constant epsilon r1, over it we have that channel of dielectric constant epsilon r2, and in the third example we have trapped image guide. So, in this case only change with the first one is that we have packaging. So, we can minimize the crosstalk between two different channels. So, for all these dielectric guides, we always face with dielectric boundary. For the first example, we have air dielectric boundary. In second example, we have air dielectric boundary. In addition to that, dielectric boundary separated by this interface, right. So, what is the problem we face? It supports hybrid mode. So, that means in the direction of wave propagation, we have both electric field component and magnetic field component, and not only that, we have to deal with all the 6 components, 3 components for the electric field and 3 components for the magnetic field. But fortunately, for different wave guiding structures, mainly we have 3 dominant components. In some cases, we will see 2 dominant component of magnetic fields and 1 dominant component of electric fields, and in other cases 2 dominant component of electric fields and 1 dominant component of magnetic field. So, we use some approximation to simplify the analysis, and we deal with only these dominant components of magnetic or electric fields. So, we will take a break, then we will start again. Thank you.